listeners, let us start our new session of Chapter 14, Oscillations. Now, let us understand simple harmonic motion. Initially, the object is available at center, at mean position, equilibrium position. Now, this object is moving into a row condition onto a single plane. So, let us consider that initially that object is moving towards the right direction and cover a distance A. It is covering a distance on negative x-axis. So let us consider its displacement as minus A amount within a time duration t by 4. Now that object, after covering a distance minus A, moving back towards the origin point. So here, now the complete t by 2 time duration has been completed and the motion has been done. Now from the origin, now it is moving in an opposite direction towards a positive x direction and covers a distance A. Now this displacement is available on positive x-axis, so we are taking its a magnitude amount of displacement plus A. So the time duration is required to complete up to this condition, that is a 3t by 4. Now from that A position, object is moving back towards its mean position. So here the complete variation has been defined within a time duration t. So that time duration t, capital T, which is known as time period. And the amount of displacement has been done, that is A. So here this variation we can define by the mathematical expression, that is x of t, that is a displacement x depending on the time t, having A cos omega t plus phi. A is the magnitude, omega is the radian frequency, small t, that is a time instant, and phi defines a phase difference. Now let us depict this equation in the waveform method. So here we are taking as a reference cos signal, because here the cos function is maximum value has been given at 0 degree angle. It means initially while the object is available at its mean position, it is getting a maximum displacement. So here we are taking as a reference cos wave. Let us define this in the form of waveform. So here initially at cos 0 angle we are having the maximum amplitude A. Then after, as it is moving towards the pi by 2 angle, its magnitude is reducing. At pi by 2 radian, that cos pi by 2, that would be 0 and we are getting 0 magnitude. Then after, that particle is moving towards the negative x-axis from the reference line positive x. So here that phase difference is available between positive x and negative x, that is a 180. So cos pi, that would be equal to minus 1, and minus A magnitude we are getting maximum in negative direction. Then after, particle is moving towards the minus y direction, and here between the positive x and minus y direction 270 degree angle is there, that is a 3 pi by 2, at where cos 3 pi by 2 is 0 and we are getting again 0 result. From there, particle is moving towards the positive x itself and the complete rotation will be there, that the angle 2 pi radian. So cos 2 pi, that will be again 1. By having that variation, we are getting a sinusoidal result having a cos function. Now, let us understand that with respect to the same time reference, if we are defining more than one wave. So here in the first diagram, 2 waves are there, both represents the cos function. Both are having a same time duration, so same frequency would be there. Initially at the reference point 0, both are having the maximum magnitude, so no phase difference is there. So here, these both waveforms are defined with the same frequency, with the 0 phase difference, having a different magnitude. Wave 1 having a maximum magnitude and wave 2 having a maximum B magnitude. In diagram B, we can see that over here, both are having a same time period, having the same magnitude, but there is a phase difference is available of 45 degree. So as we can see at the reference point 0, wave 1 having a maximum amplitude A, but wave 2 having a lesser than A magnitude and defines a 45 degree phase difference. So here in diagram B, both waves are having the same magnitude and frequency, but both are apart with phase angle 45 degree or pi by 4. While we are taking phi equal to 0, then x of t equal to a cos omega t plus phi, in which substitute the phi 0, then we are getting x of t equal to a cos omega t. This is the sinusoidal wave. Now we are knowing that after completing a time period t, the same function will be repeated. So we can define that x of t equal to x of t plus capital T time period. This function is important to define the periodicity, to identify the periodicity of the wave, and from this we can determine time period of that signal. Here the cos function is periodic in a radian form having a 2 pi period. So here, if it's a function of time t only, then we can add a time period t. But here the radian function omega t would be there, then we supposed to add 2 pi period of cos function. So omega t plus capital T, that would be equal to omega t plus 2 pi. So omega capital T time period, that would be equal to 2 pi. So omega equal to 2 pi by t. So omega equal to 2 pi by t, which is the angular frequency of single harmonic motion having a unit radian per second. Now, let us go through the another form of representation of the wave. Over here, as you can see that both waves having a same reference point, having a maximum magnitude, both are having the same magnitude, but their time period to complete one cycle is different. So these two waves are represented with equal magnitude, zero phase difference, but having different frequency. Now let us understand example regarding the same. Which of the following functions of time represent simple harmonic motion and periodic but not simple harmonic? Give the period for each case. First function has been given sin omega t minus cos omega t. This sin omega t minus cos omega t can be rewrite in the form of root 2 sin omega t minus 45. So here the phase difference is available, that is a 45 degree. Now here the function we are having sin omega t. We need to determine its a time period. So let us add its a periodic radian 2 pi. So sin omega t can be defined as a sin omega t plus 2 pi. Make the omega common and we will get t plus 2 pi by omega, which is a capital T, which gives the time period. So time period for this function we are having 2 pi by omega. This function is periodic with the time period t equal to 2 pi by omega. It is a simple harmonic motion because both individual components are having a same frequency, but there is a phase difference between these two waves. We are having a 45 degree phase. Second function we are having sin square omega t. This sin square omega t we can rewrite in form of 1 minus cos 2 omega t by 2. So here this function is periodic by defining cos 2 omega t equal to cos 2 omega t plus 2 pi. Take 2 omega common and we will get in the bracket t plus pi by omega. This is a capital T time period, which is a pi by omega. So here this function is again periodic, having a time period pi by omega. Here it represents harmonic motion with its equilibrium position. That is half instead of 0. Now let us understand simple harmonic motion and uniform circular motion. So here we are relating this harmonic motion with the circular motion. In first diagram, as you can see that, take one string and connect it one end with some object, and it's a one end, keep it in your hand and rotate it, that string. So we will get the circular motion of that object. Now while this motion is in continue, focus that motion of the object from one side, so or focus on the shadow of that movement of the object. So here we can see that from far distance, from one side, that object is moving linearly on its axis in a straight mode. So here the circular motion of that object is available, and as we are viewing, it gives you the plane motion at the edge of simple harmonic motion. Here, while we are defining that, as in the second diagram, you can see that while the object is moving in a circular motion, let us take its a position P, which makes the angle phi with respect to its a reference axis plus x. So here, the motion of the object is available from the tangent point of that particle position P, and having its angular velocity omega through which it is moving continuously. So now, after movement of that object from its initial position, it makes the angle omega t plus phi. Now from that particular point, take alignment on x-axis and give you the vector OP dash. So here, particle is moving in anti-clockwise direction onto the radius of circle A, having its angular speed omega. Initially at time t equals to 0, we are having a vector OP, makes an angle phi with the positive x-axis. And while it is moving after certain time t, it makes angle omega t plus phi. So here we are getting the function of displacement x of t, that would be equal to a cos omega t plus phi. And that P is projected onto the x-axis, having a P dash point onto the diameter, which gives you that onto the center axis, object is moving on its diameter section onto the straight line, which executes single harmonic motion. So this projection of motion of particle P onto the y-axis also can be possible. So displacement of y of t we can define as a sine omega t plus phi, because on y-axis cos function is 0. So a sine omega t plus phi we can define, and here the phase difference is available between reference line and the y-axis with the pi by 2 radian angle. Right. Let us understand its example. The figure used below depicts two circular motions. The radius of the circle, the period of revolution, the initial position and sense of revolution are indicated in the figure, as you can see over here. Obtain the single harmonic motions of the x projection of the radius vector of a rotating particle P in each case. Let us take case 1 first. So over here, as we can see that at time t equals to 0, OP vector is there, which is available at 45-degree angle. So that pi by 4 radian angle is available with respect to its reference line plus x-axis. After time t, the particle is moving ahead at another point P. So here it covers the angle 2 pi small t by capital T, that is omega t. So it covers an angle omega t in anti-clockwise direction. So total angle it makes with the axis, that is omega t plus phi, that is omega t plus pi by 4. Z phi is available over here as a 45 degree. So x of t equal to a cos omega t plus phi that is x of t equal to a cos 2 pi by t plus pi by 4. Now here, as you can see in the first diagram, capital T is given 4 seconds. It means time duration is 4 seconds. So here omega is 2 pi by capital T, and substitute the value of time period T as a 4 second. So we are getting x of t equal to a cos 2 pi by 4t plus pi by 4. So here for the single harmonic motion having an amplitude A, having a time period 4 seconds with its initial phase difference pi by 4. Now let us calculate for the second circle. Here at a time t equal to 0, OP, that vector is available onto the y-axis. So with respect to positive x-axis, it makes initial angle pi by 2. Now after time t, while it displays at clockwise direction, so here the direction is in reverse. So here our angle is available is phi minus omega t. If the particle is moving in anti-clockwise direction away from the plus x-axis, then it makes the angle omega t plus phi. But here, while the object is moving towards the plus x-axis in a clockwise direction, then it makes minus omega t plus phi. So now our equation becomes x of t equal to b cos minus omega t plus phi. So here omega is 2 pi by capital T. By substituting those values, we are getting that equation x of t equal to b cos phi minus omega t, and omega is 2 pi by capital T. Here the capital T time period is given 30 seconds. By substituting those values, we are having that equation b cos pi by 15t minus pi by 2. So here we are having a time period 30 seconds by having a phase difference minus pi by 2. Now let us understand velocity and acceleration component in SHM. Here while the object is moving in a uniform circular motion, its velocity is or the speed is available as v, and its angular speed is available as omega. It is moving onto the circle having a radius a. So it's a linear speed or velocity v equal to angular speed omega into a. So here we can define v equal to omega into a. So here the direction of velocity is available at time t with the tangent component of that circle at the point. Here the instantaneous velocity is available at p dash onto the reference axis plus x axis. So omega t equal to minus omega a sine omega t plus phi. Here the negative sign is defined that a particle is moving away from the reference line plus x. So velocity is available v of t equal to minus omega a sine omega t plus phi. And here how from this graphical representation we able to get its velocity value. Now earlier in the displacement topic we have defined the displacement equation dx of t equal to a cos omega t plus phi. We know the velocity is nothing but change in position per time. So delta x by delta t. Here the continuous variation is there. So instead of the delta we can take a differentiation. So without referencing a graphical method from the displacement, by differentiating the displacement with respect to time, also we able to get the same equation, velocity equation v of t equal to minus omega a sine omega t plus phi. Now while this object in which continuous direction variation is there, so acceleration is available, that is a centripetal acceleration is available and object continuously moving onto the circular form. So here that acceleration is available having the magnitude v square by a, the linear acceleration, or angular acceleration we are having omega square into a. This acceleration is always directed towards the center along the vector OP, and that particle P onto the circle, it is projected onto the plus x-axis having a P dash position. So here acceleration we are having maximum amplitude omega square a representing a circle form, that is a function cos omega t plus phi. Here again the negative sign defines that particle is moving away from positive x-axis in the opposite direction. So a of t is minus omega square a cos omega t plus phi. And we know a cos omega t plus phi is displacement. So that would be equal to minus omega square x of t. Now we know acceleration is nothing but change in frequency, change in velocity per time, that is a delta v by delta t. Again, for the continuous variation, instead of a delta difference, we can take differentiation. So if we are doing differentiation of velocity with respect to time, then again we able to get same equation of acceleration. Here acceleration is directly proportional to the x of t, but having a negative sign in proportion in between. So we can say that when distance gets increases, acceleration gets reduces, and when displacement x of t is less than 0, then a of t greater than 0. So displacement is available from minus a to a onto the linear diameter axis, and based on that acceleration is available towards the center. Now in all these three equations of displacement, velocity and acceleration, let us substitute phi equal to 0. We are avoiding a phase difference. So these equations can be rewrite as x of t equal to a cos omega t, v of t equal to minus omega a sin omega t, and a of t equal to minus omega square a cos omega t. These three functions are represented over here in the graphical method. Here x of t, which is a cos function, so it's a 0 reference line having the maximum amplitude. V of t, that is a minus omega a, means having a magnitude omega a, but which is negative having a sine function. Sine function defines that at a reference point 0, its magnitude is 0. So based on that, velocity time wave is available, that is sine function, but initially it represents a negative magnitude. And a of t, that is again cos function, but having its magnitude omega square a, initially it is negative, so it is started from negative component. Now we can see that displacement is varying between minus a to a, velocity is varying between minus omega a to plus omega a, and acceleration is varying between minus omega square a to omega square a. And with respect to displacement x of t, if we define the phase difference x of t and v of t, then phase difference is available of pi by 2, because displacement function is cos function, velocity function is sine function. So in between them, pi by 2 90-degree phase difference is there. And between x of t and a of t, displacement and acceleration, the phase difference is available pi, that is completely in opposite direction. Now let us understand example regarding the same. Here the body oscillates with SHM, simple harmonic motion, according to the equation x equal to 5 cos 2 pi t plus pi by 4. Here t is given 1.5 second. Then calculate displacement, speed and acceleration of the body. Here angular velocity omega is given as a 2 pi. right? We are having the standard equation x of t equals to a cos omega t plus phi. So omega equal to 2 pi, capital T we are having a 1 second, and instantaneous time is given, that is a 1.5. So x of t equal to a, that is a phi, cos omega, that is a 2 pi, small t, that is a 1.5 second, and phi, that is a pi by 4. By substituting those values, solve that one, and we will get displacement minus 3.535 meter. Now we want to determine its a velocity. So what is the equation of velocity? Minus omega a sine omega t plus phi. So minus omega, omega is given 2 pi, a is 5, sine omega means 2 pi, t means 1.5, and phi, that is pi by 4. By substituting those values and solve it, we are able to get its a speed 22 meter per second. Now the third quantity we need to determine, it's acceleration. We are having that equation of acceleration, that is minus omega square a cos omega t plus phi, that is minus omega square x of t. X of t displacement we have already covered. We have already determined. So minus omega square into displacement. Omega is 2 pi. So minus 2 pi square into minus 3.535 meter will give you the acceleration 140 meter per second square. Clear? Here we are going to end the session. Hope you understood. Thank you.